Hello everyone, this video is for lecture 3. This is the reading you did. I'll go over the reading and try to help you make it more clear for you. So the idea is electric field and how it applies force to charges. We already know there is forces between charges, but it turns out each charge alone has a field around itself. So if I have a positive charge here plus Q, let's say, it will have an electric field around itself even though there's no charges around. And any charge that comes by, any other charge, could be positive or negative, that comes by, let's call this a test charge. It's usually taken as capital Q plus, and put it close in this electric field, it will feel it. And here's how we represent this electric field theory. And it's a real thing, it's not an imaginary thing. Every charge has this effect around itself. So the use the force and so on is actually true. And this figure here is showing how defense department is planning on building a force field that will protect the equipment and planes from any type of attack, and maybe true in the future. This figure is again showing 4 fundamental forces. Gravity is the weakest force. We have a question on a video I posted earlier comparing the force between two protons, gravitational and electromagnetic, or electric force in that case, and you will see that the electric force is very much stronger than the gravitational force. So if we put a charge in an electric field, here is the force that is applied to it. It's E times Q. That's how I want to show it to you. Actually, from here what we find is the force applied to that charge is equal to the charge itself times the electric field it put in. That's easier to remember, but we can turn it around and write it that electric field is equal to force applied to that charge divided by the charge, as it's shown in here. That's one simple idea in here. And this part over here talks about how bees can sense the electric field change if they are going towards a flower, and let's say a flower has some sort of electric field around it. It's shown as negative here. So electric field would be towards the charge. And if some other bee visits this flower, it will change its overall charge. So this electric field will change and this bee will sense it and turn back, go to another flower. This picture is also showing the same idea here. Flower here, electric field, and this bee senses an electric field as it moves towards it. This table is overall summarizing the logical physical values of electric field inside a current carrying wire. It's of the order of 10 to minus 2, so about 0.01 or around there. And the unit for electric field is Newton per Coulomb. Keep that in mind. We always want to keep the units. We said F is equal to QE, right? And we know F is Newton. SI unit is Newton, not Coulomb, Newton. Charge is Coulomb. And electric field can be solved from here by dividing each side by charge. So E will be force divided by charge. And force is Newton, charge is Coulomb, so electric field will be Newton per Coulomb. Going back to values, around the Earth's surface we have 10 to 2 Newton per Coulomb. Near charged objects by Robin, 10 to 3, 10 to 6, and so on. You have a list here. You can go back to check if the answer you found to a question makes sense. Electric field model tells us by measuring the force applied to a charge at any point, we can find the electric field at that point, as E is equal to F on Q, charge on that Q divided by the charge itself. After doing that, the electric field will be in the same direction as the force applied to a positive charge. So we put a positive charge, measure the force on it, divided by the charge, that's the magnitude of electric field, and the direction of the electric field is the same as the force direction for a positive charge, and it's opposite direction for a negative charge. We can turn this around as well. If we know the electric field in a region to the right here, as you see, then we can say if I put a positive charge in this region, it will be pushed in the same direction as the electric field, and if I put a negative charge, it will be pushed in the opposite direction, and each have force that is equal to Q times E. Over here we will use absolute values again. We won't worry about the charge sign. We'll keep in mind positive charges are pushed in the same direction as E. Here we see they are same, and negative charges are pushed in the opposite direction. E is to the right, negative charge is pushed to the left, opposite. So always keep that in mind. Find the direction of forces and then calculate the force using QE, absolute value QE. We already know this force. This is actually Coulomb force, F Coulomb, and we can write it as Q prime in this case over R squared. The test charge is called Q prime. Q is our source charge that creates the electric field. Using this equation and the new equation we learned that F is equal to QE, we can solve for E here. Q prime E, sorry, in this case it's Q prime that we are interested in. And we can solve for E. We'll have an equation for electric field due to a charge Q at a distance R to be KQ over R squared. This equation here. So if I'm given a charge and I don't know anything else, I know that charge and distance, I can find the electric field in that distance. And this page is kind of summarizing what we learned. Electric field of a point charge. If we put 2 point charges inside an electric field that is to the right, positive charge will have a force that is the same direction, let's call this F positive, and negative charge will have a force that is in the opposite direction. Another information is if we have a positive charge, electric field is always away from that positive charge. If I put, for example, a negative charge here, the force will be opposite direction to E. So this is E, this is, let's call F negative, force applied to negative charge. This is an example here, finding the electric field of a proton. The electron in a hydrogen atom orbits the proton at a radius of 0.053 nanometer. That would be our R. So if I want to symbolize that, I have a proton. Let me put as plus P, and electron orbits it. Electron minus, right? I'll call this minus E. Plus P actually has a charge of plus E. If you remember, they each have the same charge in magnitude and opposite sign of the charge. And the distance turns out to be R. I'll put that over here. 0.053 nanometer. Nano is always 10 to minus 9, so I'm going to convert this to meter. My SI unit, remember, meters SI, So 0.053 times 10 to minus 9 meters. So electron is orbiting the proton here. What is the electric field due to the proton at the position of electron? So I'm looking for the electric field of this proton. It will be away from it, right? It's positive. Let's draw some symbolic lines. And I know the distance, I know the charge is the proton. It has a plus E. And the plus E charge, I check my notes and see it's equal to 1.6 times 10 to minus 19 coulomb. Notice here electron is pulled towards proton, and I can decide from there that the force is towards proton, right? This is also the same thing as opposite charges attract. So force on this electron is towards the proton. And it agrees with what I learned new. Electric field and force are in opposite direction. E field is outward and force is inward with respect to proton, opposite to the electric field. Now if I want to solve for the electric field, is K Q over R squared, and my Q for the Q proton, right, is equal to E. I put in all the numbers. My K is 9 times 10 to 9 Newton meters squared over Coulomb squared. My E is 1.6 times 10 to minus 19 coulomb. This is 19 here, not 9. And the distance is given as 0.053 times 10 to minus 9 meters. Let me rewrite this as well. It's not looking good over there. Sorry about that. 0.053 times 10 to minus 9. Sorry folks, my computer is not reading me well here. Let's put this again in meters. 0.053 times 10 to minus 9 meters. I can write this in this terms as well. So 0.053, I can move 2 steps right. 5.3, if I move 2 steps right here, I have to deduce 2 points from there. So that's equal to 0.0, go back. 5.3 times 10 to minus 11 meters. So that's what they put in here. Put in all the numbers, we'll get this value for the electric field. Please do solve this for yourself. Have it in your notes as an example to learn it better. Now, does this value make sense? Then to 11 was the range of electric field inside atoms. If we go back to our table here, so that will help us understand that what we found makes sense. If I would find 10 to minus 11, perhaps I made a mistake. Always do check the tables. They're often given in your book to see if your answer makes sense. So I quickly already discussed this. Electric field lines are away from positive charge towards negative charge, and they would get larger as we move towards the charge because they are inversely proportional to distance. So we can symbolize them as vectors here. Small vectors outward and large vector close by. This picture is also showing the same thing. Electric field of a positive always away from positive charge, and as we go away step by step, we see that the vector is decreasing, and the same thing here towards the charge. As we go far away, electric field decreases. This is an example, a logical example, at which point the electric field is stronger, A or B. A is closer, so stronger, B is farther. I can also put my equation for electric field to understand this. KQ over R squared large R will give me small e. So point A is a stronger electric field. This one we already went over in class. What I'm looking at is electric field. Overall charges are the same. I'll look at the distances and directions too. So this distance is 2r, this is r. If I call these charges q and q, I'm going to show the electric field by negative charge with a red. Will be towards my charge. Put it as E. And the electric field due to positive charge, let me use green, it will be away, and it will be smaller than E. It will be significantly smaller than E. Actually, E over 4, because here is my equation. KQ over R squared. Double R, 4 times smaller E. So overall here I have a field to the right. If I call that positive, left will be negative, and addition will give me an overall left. Remember, as we add the vectors, we actually subtract them if they are in opposite directions. So this will be E total here. Let's call this E1. So the first one is to the left. They actually give me a very bad clue here. Only option B has first one to the left, so I could just cheat and say this should be the answer. But let's go through them all. Second one. This time negative is farther away, so my negative to the left will be smaller. And I'll call this also E over 4, twice larger. And the positive will be to the right. Why positive is to the right again? Because positive has electric field always away. It will be E now. The magnitude will be the same, but this time it will be to the right. If I was comparing first and second, I would say they have the same magnitude. But overall, I'm going to have an electric field E2 to the right. The second is right. So this dude is correct here. Stick it in. Left, right, we got that right. Third one, we have two positives. And I'm going to show their electric field. The closer one will be away, E. And the farther one also will be away, but smaller. Let me try to do a better job here. Not E, actually E over 4. Let me extend this a bit more so it will be larger. So overall I'll have a left direction. Also agrees here, but quite larger, E plus E over 4, because they both are in the negative direction. And the last one, I have a negative charge on the left that will have an electric field E towards itself. And the one on the right will have electric field E towards itself. They both are same charges, same distance away. So these E values are the same, they cancel. Total will be 0 if I call this E4. Will be 0. And E3 will be overall to the left. Let me draw that as well. And it will be actually the largest electric field to symbolize it this way. And the answer is B. What is the electric field at the dot? Direction only here. Pretty simple question. A negative. I don't know why I don't have answers for these. Some problem. Negative electric field will be towards, so the answer should be B. Yeah, I should correct this actually. I don't know where the other options are, but the answer is B. Multiple charges. If we have multiple charges, what we do is we show all the electric fields, keeping in mind electric field is a vector. And add them. As we add, We add vectors. Direction matters. For example, this question here is a nice question. I have Q1, Q2, Q3. I'm just looking at this overall. I don't know their values, but I can draw. What is the total electric field at this point? All charges are positive, so all charges have electric field away from it themselves. So Q1 would push. This would be my E1 here, as you see in the figure. Q2 would also push, and Q3 would also push. Overall, I can say this is already along the diagonal. If I complete a parallelogram here, E1, E3 will also add along the same diagonal. They won't be the same at the length perhaps, but this will be E1 plus E3. And overall, I can say the total electric field will be along that diagonal. If I had the values, I could calculate it as well. Let's put that as a green line. But I can safely say it will be in this direction. So that's vector addition again, similar to what we do with the forces. We will call this E total. In this case, I will need to take components because they are easier. They are perpendicular. One is along diagonal. If I need to, I'll take components and add them. Sometimes the question could be as easy as this figure here. Plus, plus, minus, minus charges. What is the electric field in the center? It will be 0 in this case. Because the same amount of charges, same distances will apply the same electric fields. Let's look at plus, plus. E1 away, this direction, equal to E3, cancels. Let's use lines here to make a better job. So E1, right? Same charge, same distance, same electric field, cancels. 0. Minus minus E2 is towards itself, same distance, same charge, E4 towards itself, they also cancel, so we have a 0 total field. This one here is an electric field dipole. Again, if we have one plus, one minus charges close to each other, we have a dipole. You read about this in the first lecture as well. Sometimes there are natural dipoles. Water is a natural dipole. Let's see what this question says. A dipole consists of a positive and negative charge separated by 1.2 centimeters. That would be my distance, right? In between distance, but the question is asking, I guess, what is the electric field here? What is the electric field strength along the line connecting the charges at a point 1.2 centimeter to the right of positive charge here? What is the E here? What we do in this case is we find the electric fields due to positive and negative charges at this point. Positive charge is closer. Actually, it has a distance of 1.2 centimeters. So it will have a larger electric field away from itself. E positive shown here. Negative charge, let me choose a different color here. Negative charge is farther away. It's actually twice the distance, 1.2 plus 1.2, 2.4 centimeters away. So it will have a smaller electric field and it will be towards itself, shown here. That would be E minus. So we're going to find positive electric field and negative electric field and add them as vectors so they will have signs, and we'll have an overall electric field in this direction, right? Positive is larger. Remember how we were adding the vectors? Head to tail can be used here. We have the first vector, take it as is, E positive, and at the end of it add the second vector over here, E negative. This way actually they are canceling. let me do a better job here. Okay. My computer doesn't like the eraser, I guess. Alright, E plus E minus, add them. Overall vector, total vector, will be the one combining the beginning of first to the end of the other, the second. Here we go. That's our E total. It will be to the right, in the same direction as the larger vector, and here's how we just add them. We have a positive number, negative number, add them, and calculate those values, of course. Let me put this here. E plus will be K, let's call this Q plus over 1.2. Let's convert those to meters as well, right? We want to use meters, not centimeters. So 1.2 centimeters divided by 100, 0.012 meters squared, and E negative will be K Q negative divided by 0.024 meters squared, 0.4 centimeters. Always use meters. The charges are given here. Q minus and Q plus. We could also call them Q1, Q2. And the solution is directly done in here. K is this. This is Q plus divided by distance squared in meters. K, Q minus distance squared in meters. And this should be our answer, and it's positive. What is the direction of electric field here? We have positive, negative. Here is the point, negative towards itself. Let me draw this with a line. Let me draw it larger. I'm looking at only a direction. I'm going to call this E1. I'm going to call this charge 1, and charge 2 is plus. Plus will apply an electric field away from itself. Let's draw that green maybe. But it will be smaller than E1 because it's farther away. Significantly smaller because it's about twice farther away. But overall, when I add these two vectors, my total vector will be to the left, right? Because the left vector is larger, and the answer will be B. There could be different types of electric field values for multiple charges. We'll do some examples in class in LC. I'll also ask you some other on team assessment. But this one would be another example. Plus charges, what is the electric field here? We know this guy pushes down, down, and overall I can easily see that the X components will cancel here because they have the same angle, same distances, same charges, right? Q plus minus. So E plus X and E minus X would cancel, and I can guess easily that the electric field will be down here. You will do a calculation of this in class soon. Alright, that's all I'm going to tell you about this, and we'll go back to it in the future.